Now we know that at AC steady state, when a transmitted wave travels down a transmission line and encounters an impedance boundary, such as the interface between a T-line and an electrical load, some of the electromagnetic wave is going to be transmitted to the load, but some of it is going to be reflected back towards the source. The reflection coefficient, gamma, relates the ratio of the reflected wave to the amount of incoming wave. So gamma is just the ratio of V bar minus to V bar plus. In essence, it's what percentage of V bar plus has been reflected. The important thing to remember is that that incident wave and the reflected wave, they're traveling along the same conductor, and therefore superposition of the two waveforms is going to occur and create what is known as a standing wave pattern. Effectively, what is happening is the cosine forward wave is adding to the cosine of the reflected wave. What we'll see, though, is that this wave pattern that gets established is not traveling like the two wave components. Instead, it's fixed in position, and what is called a standing wave is formed, meaning that the wave remains constant in position. And so, to better understand this phenomenon of the development of a standing wave, I want you to consider a voltage wave that's traveling on the T line that has 1 cosine of omega t minus beta z. So it's got an amplitude of 1, it's traveling along a lossless conductor because there's no attenuation, and is traveling from the left to the right. Let's also assume that the reflection coefficient at the load is equal to 1 at angle 0, meaning that the entire wave is reflected and no phase shift is introduced. That means the reflected wave is going to be 1 cosine of omega t plus beta z, and no phase shift is introduced. So this is the incident wave, and this is the reflected wave. Therefore, along the transmission line, the total voltage is going to be V of z comma t, 1 cosine of omega t minus beta z, plus 1 cosine of omega t plus beta z. Since there's two waves, the total voltage is just the sum of the two waves. The beta terms inside of the cosine function have opposite signs because one is a positive traveling wave and one is a negative traveling wave. And because the argument of the cosines are different, we can't directly add those two. And instead, we have to use the law of cosines to add those two. And so you probably have seen this, but I'll just refresh you. Cosine of x plus the cosine of y is equal to 2 times the cosine of x plus y over 2 times the cosine of x minus y over 2. So we're going to use that. We're going to add those two cosines. So v of z comma t is going to be equal to 2 times the cosine of omega t minus beta z plus omega t plus beta z over 2. And then that gets multiplied by the cosine of omega t minus beta z minus omega t minus beta z over 2. So v of z comma t is therefore equal to 2 cosine. We see that that beta z and that beta z cancel out, so we have omega t plus omega t, which is 2 omega t, divided by 2 is just omega t. And in the second term, we have omega t minus omega t, and minus beta z, so that's 0 minus 2 beta z divided by 2. So cosine of minus beta z. Remember that cosine is an even function. Cosine of minus theta is equal to cosine of theta. And so therefore v of z comma t is equal to 2 cosine of omega t times the cosine of beta z. So this shows that in the composite voltage waveform, the resulting cosine term, we still have a cosine with time dependency, and we still have a cosine with a distance dependency. But now it's not a traveling wave anymore. We have the multiplication of two waves. But unlike up here, it's not in a traveling wave form. The omega argument and the beta argument are no longer arguments of the same cosine. And what this results in is a standing wave pattern. So I've got a little video here to play of what a standing wave pattern actually looks like. So the blue line here in this video represents the incident wave. It then gets reflected back because it encounters a impedance boundary at the far right-hand side. The red line represents the reflective wave. The black line represents the addition of the blue line and the red line. And so whereas we see the blue line traveling from right to left, and we see, from left to right, and we see the red line traveling from right to left, what happens with the black line is that it adds together, and we get this oscillation in space and time. And they add together to form this black wave, and it's called the standing wave because although it changes amplitude over time, like if I were to measure right here, its amplitude's changing, it's not traveling through space like the red and the blue waves are. From this video, we can see that there are a couple locations. We see that there's a location 0, this location here, which is lambda over 2. We've got 3 lambda over 2. We see that there's always a the amplitude of the wave is always at a minimum, and these are called the nodes. There's also locations where there's a maximum and a minimum occurring at the same point. Those are called antinodes. So we see this antinode is going from a peak value to a minus peak value, and we see this node, its amplitude never changes. The distance between two nodes in a standing wave is always going to be lambda over 2, whatever the wavelength of the incident and reflected waves are, divided by 2, and the distance between two antinodes is always going to be lambda over 2.